want to start and stop it because it's easier for bookkeeping. Have we done the two objects colliding into each other, the three things they have in common? I'm getting a lot of blank looks and some shakes of the head. All right, so I have two objects here coming towards each other. They will collide at some point. Let's just say they collide right here. So that's the point where they meet. And the boxes that I'm drawing down here are supposed to be the same size as up here. I just don't have the talent to actually duplicate it properly, but that A and B are the same size. So they clash, they're together for some tiny amount of time, and then they separate. So that's basically where they are when they separate. And in this particular scenario, I'll have them bounce off each other, although they won't necessarily bounce off each other. If you imagine truck and bug, they will not bounce off each other. So the question is, while they are colliding, while they're touching each other, there are three quantities that are the same for both objects. And to add just an element of danger to it, can you do it before the physics victim is hanged? Sorry.
Aren't they exerting the same amount of force onto each other?
Yes, that's one of them. And thank you for saying amount of force as opposed to the same force. They are not exerting the same force on each other. Why not?
They're going in opposite directions.
Yes. But it is the same magnitude of force, and so that is one of the things they have in common. I'm just going to do the shorthand notation. The force on A from B is equal to the negative of the force of B on A. Technically, what Olivia said is this, but we'll take it that one step further. This is just shorthand notation. This is Newton's third law in symbolic form. And I guess, Gina, you've got the steepest angle from that side. Is this board blocking it?
No.
Okay. All right, one down, two to go. And if you take too long for one of them, I'm going to give my most obscure clue for any clue that I ever get.
What are we doing exactly again?
There are three quantities that are the same for both of these. While they're colliding, while they're touching, there are three quantities that are the same for both. And I would like you to tell me what the three are. We have one of them already. Same amount of force.
The magnitude of friction within a place?
So let's just assume that all the forces are covered. Whatever force they're exerting on each other, that's already summed up here. So we don't have to start going down the list of specific forces.
Same amount of acceleration in opposite directions.
If they have the same magnitude of force, their accelerations are not necessarily the same. Think of, again, bug and truck. If they collide, the bug is going to accelerate far greater than the truck will.
Did you say they were the same size?
I did not. What I was saying is that The size of this box is supposed to be the same size as that box.
Okay.
All the A's should be the same size, I just can't actually draw it that way.
So A and B are different sizes?
Yes, or, unknown.
Okay.
I will say that the one for which I generally give the obscure clue is so incredibly obvious, people don't think about it.
A change in motion causes a change in velocity, which causes acceleration.
Okay, what is the answer to the question, though? What, are you just doing a scatter shot of all those things that you just mentioned?
Right, I'm trying to.
Because that
Newton's
was already
second
taken
law.
out.
Yeah, because of that hint, attributing finger.
Yep.
Newton's second law, and it has something to do with this, I'm assuming.
Newton's second law is the reason why this is not true, because if it's the same magnitude of force, if the masses aren't the same, acceleration can't be the same. Although, technically, they would be in opposite directions, so the vector one would not be the same, the scalar one can't be the same. Because of, the masses are not necessarily the same. Word it out.
Do we know anything about the speed, or is that also unknown?
About what?
Speed.
Their speeds may or may not be the same, their velocities definitely are not the same.
Right.
And given this particular scenario. Although if you've seen Mad Max, you know that the velocities don't necessarily have to be in opposite directions in order to collide. You could have pursuit, or I guess intercept. If you haven't seen Mad Max, have you missed anything? You've missed some things. There's a lot of dull section in there, but the ending is just, was satisfyingly brutal, for exam time. All right. There are only a limited number of quantities we've studied. Why at 5 all day long? Somebody,
No, I was just saying, I think this is beyond what I've studied.
The amount of time each one takes to, the amount of time it occurs for, the amount of time it takes for the collision to occur is the same for both?
absolutely. They touch each other for the same amount of time. That's the obvious one. That's the one that's so obvious, people usually don't think about it, and it's usually the last one people come up with. And my obscure clue is, it's the name of a Bobby Sherman song. So the time that A is touching B is the same as the time that B touches A, while they're colliding. So basically from that time right there. So if people need a visual, they don't, I got these two options. Absolutely brilliant hand-eye coordination there. And it doesn't look like that way in the video that somebody tampered with it. Sending any thoughts out there?
I was gonna say the amount of work done is the same. I guess that's the same as force maybe?
The amount of work,
It's non-conservative?
The amount of work that each does, one will be the negative of the other.
Okay.
So, we're leaving into that, so. The reason why amount of work is not sufficient, like amount of forces, because force is a vector, work is a scalar, and so amount could be a negative number. Which it would be for one of them. All right. I've gone through this, and there's, even on non-quiet days, often it devolves into a read my mind exercise. I've also gone through, this is the answer I want to get, how do I ask the question, and what I got back was exactly how I'm asking it, so I don't know how to do better than what I've got there. But B, if we think about the center of mass of B, center of mass of B goes that far. Center of mass of A, well, despite the way I've drawn it, would be the same. They both displace the same amount. All right. Why do I even bother doing this? If I look at those two, I'm dealing with momentum and impulse. If I look at these two, I'm dealing with work and energy. So chapter 7, chapter 8. I'm going to just do a quick little derivation here. Do a little multiplying here, so let me just do force times displacement. This is a dot product. There are two types of multiplying. One's a dot product, the other's a cross product. This is the dot. But master set 7 is dealing with this stuff, right?
Yes.
Okay. And then no questions on master set 7. Can I conclude that I don't need to go over any of this?
I would,
You would conclude that?
I would.
Okay. All right. Oh, Olivia?
Well, I was actually gonna ask, I get like the conceptual thing of conservative and non-conservative forces, but
Right.
I was hoping like we could have more, like, and we have examples for conservative forces and non-conservatives is just like all other things. Can you maybe get like, a tad bit more specific on like when would a non-conservative force be 0, when would it be negative, or when would it be positive?
Yes, that part of the master set.
Yeah.
The question, okay, when is, so it ultimately comes down to when is a dot product positive, negative, or 0?
Okay.
If we took this and we kept going, we'd eventually end up with, if this is the total force, that's the total work. And so if we plug in mass times acceleration, we got the dot product, we ultimately end up with the change in kinetic energy.
Right.
So, well, I'm hoping everybody has seen the video. You're about to really impress me. What's the formula for kinetic energy?
Half mv squared.
Not quite the unison I was hoping for, but I do appreciate the response there. Let's try in unison. Because again, as the video says, the one formula I expect you to know cold. What's the formula for kinetic energy?
1/2 mv squared.
Wow, that, I think I'm going deaf in one of my ears. Everyone, and I am serious. What's the formula for kinetic energy?
1/2 mv squared.
Okay, much better, thank you. Although I would expect it to refer to you a little bit louder there, Brian. Next time. All right, so if my total work is positive, that means my kinetic energy increased. Since the total work is equal to the change in kinetic energy is associated with how fast it's going. So if I have a mass and the speed increases, the total work has to be positive. Well, let's think about what that would mean in terms of a force on an object. If I have an object that's going to move from here to here, so its displacement is a vector that long going to, or representing that distance in that direction. Which way would the force need to be applied to the object to get it to go faster? All right, from the hand gestures, yes. You basically are pushing it in the direction it's going. If we wanted to slow it down, in other words, do negative work, which way would the force need to be applied?
Push against it, so opposite
Okay?
that.
And if we don't want to change the speed at all, which way would the force need to be applied? Or down. And that's what it comes down to, is that, at least for this, starting out as this as an example, if at least part of the force, if part of the force same direction as the displacement, work is positive. If the force is perpendicular to the displacement, work is 0. And if the force is, if part of force opposite the direction of the displacement, work is negative. Now, I did this in terms of the total work being done, but it also applies if the conservative, part of the conservative force is in the same direction, then the conservative work is positive, and so on. So in that, because this is the one, you've got that table there of picking out when work is, conservative work is positive, negative.
Yeah, it's
Zero.
conservative and non-conservative, and then positive equals 0 or negative.
Okay. So it's just, so when I'm grading that, for the total work, I'm going, is it speeding up or slowing down? Or not changing the speed at all? So for the non-conservative work, well, actually, for conservative work, this is a little bit easier for grading, is we got 3 work energy relationships. The total work is equal to this. The conservative work is equal to the negative change in potential energy. So if this is positive, the change in potential energy is negative. If conservative work is negative, the change in potential energy is positive. And then 0 and 0. And then for non-conservative, that gets a little bit tricky, because sometimes people give situations where I'm going, I could go either way. That the non-conservative work is equal to the change in energy, which is the change in kinetic plus the change in potential. So either I have to go through the situation and go, all right, what's happening to the total energy, or what's the non-conservative force here doing work?
So non-conservative work examples would be like friction, tension, normal force, other, mechanical, and thermal.
No, be careful on that one. Mechanical work is just, this is mechanical energy. Mechanical work would be, actually, it's sort of undefined. Mechanical energy is kinetic energy plus potential energy. The differentiator from just energy, energy would include rest energy. Mechanical energy just ignores rest energy, which is the energy inherent in an object because it has mass. Rest mass, I should say. Thermal energy is just a name used by people in thermodynamics and chemistry for kinetic energy.
But is that what you were, like, more examples of non-conservative force? Cause I also had trouble with that, cause in the video, like she
Yeah, cause
said,
it's just like
it
every
just
other
like,
thing.
it's like the rest of them, like other, so gravitational.
Gravity and ideal spring slash
Right.
elastic.
Yeah, that's pretty much, you got those two right there, gravitational force and ideal strength. A non-conservative force doing negative work, it stopped. Or, actually, when I hit it, it sped up, I exerted a non-conservative force on it. Because, and if you think about the wording there, non-conservative force, energy is not conserved. So, right now, it has some potential energy, or not, depends on where we define, how we define it. It has 0 kinetic energy, 0 joules of kinetic energy. When I tap it, it suddenly gains kinetic energy because it speeds up. I'm assuming the mass did not, we didn't lose any mass. And because it sped up, it gained kinetic energy, therefore positive work was done, and it happened to be non-conservative. Is that, have I answered your question, or have Sarah and I answered your question?
Yeah, I believe so.
Okay.
Could we go over on how to start number 7?
Which was number 7?
It's talking, a conservative force and a non-conservative force are applied to an 8 kilogram object between the positions. And then if no other forces act on the object's initial velocity is given, and then what's the object speed after 5 meters? Going in the X direction.
Alright, so we have the total work equal to the change in kinetics. The non-conservative work is equal to the change in energy, mechanical energy. The conservative work, negative change in potential energy. And what did we look at the wording again? Number 7. Alright, so it gave you the force, and the non-conservative force, and alright. So I have it going from, I'll just use different numbers here. So I said the conservative force was 5 newtons I hat minus 2 newtons J hat. The non-conservative force is, I think, 2 newtons J hat